All right, so previously we just looked at these factors, the constant gain, the simple pole and the simple zero, the origin pole and the origin zero, and you're probably thinking, what in the world did we do all this for? Well, this is what we did it for. We did it so that now we can decompose this transfer function into its factors. We can sketch the magnitudes of each individual factor, and then we can add them together to get the overall magnitude plot for this particular transfer function. You know, we remember previously, if I go back, we were going point by point at multiple frequencies to derive the behavior of this transfer function, which is very tedious, right? I had to derive the magnitude mathematically, I had to derive the phase mathematically, and I had to go and put these functions into my calculator, and I had to individually plug these omega values into my calculator so that I could obtain the decibel values of of the magnitude of the transfer function at that frequency. This is very tedious. This is not how we want to plot magnitude and phase. We want to do it in a much simpler way. And so what we're about to do with everything we've learned is we're going to plot it in a much simpler way that generalizes really well to much more complicated transfer functions than what we've already seen. Okay, so they have this written as h of omega. I don't know why they do that. It could be written as h of j omega. It could also be written as h of s, right? If we let s equal j omega. So I'm going to write it as h of s equals 200s over s plus 2, s plus 10. I'm only doing this because when I wrote out the factors, I wrote them all in terms of s, right? So I just want to stay consistent. But you recall that for frequency response, we can just say that s is equal to j omega. Okay, and so if I want to get this into the standard form that we talked about previously, I have to, the top looks fine. There's nothing I can do there. But on the bottom, I can factor a 2 and a 10 out of those two terms. So I'm going to say 2 times 1 plus s over 2, and then 10 times 1 plus s over 10. And so now I can group all my constants into one single constant, right? 200 over 2 times 10 times 1 over 1 plus s over 2 times 1 over 1 plus s over 10. And now I have my transfer function split up into 3 different factors here. I've got, 4 different factors. Sorry, there's an s in there too on top. I don't want to forget that. Let me move these. And I'll put an s here. So those are my 4 factors. 200 divided by 20 here just gives me 10. Then I've got an s, I've got a 1 over 1 plus s over 2, and then I've got a 1 over 1 plus s over 10, right? And so this is my transfer function, kind of rewritten in standard form and broken up into the factors that make it up. And so this is going to be where we need to now assess what each of these terms actually are based on what we've covered previously. And then we can sketch the magnitude response of each of those. And then at the end, we're going to add them all together to get the overall magnitude response. So if that's still not clear, we're about to do it, and I think it will become a lot more clear. Okay, so let's start with the value 10. Okay, if you remember from these factors that we were looking at, a constant value, k, right? If we want to write out the magnitude of that, it's just going to be 20 times the log of that constant k. So for us, the k value is 10. So for the magnitude, it's just going to be 20 log of 10, right? And if you remember correctly, the log of 10 is just 1, so this is just going to be 20 dBs for my constant gain, okay? So I would go here, and for the constant gain term, I would go and write, I'm going to write a dotted line that just goes across the magnitude plot at 20 dBs for all frequencies, okay? And so that's from my constant gain k, right? The next one is just s, which, if you remember correctly, is an origin 0, right? If I let n equal 1, it's just s. It's an origin 0, and what does that do? Well, it goes up at 20 dB per decade, and it crosses 0 dBs at omega equals 1. Okay, so let's go and sketch that. And if it goes up at 20 dB per decade, I need to make sure that I put a point at 1, a point at 10, that's 20 dB higher, and then a point at 100. And then I can just kind of trace myself a little line here. It's as linear as I can make it. Okay, and so that's going to be the effect from my origin 0. Okay, so we've taken care of the constant k, we've taken care of the origin 0, right? This is my origin 0. Actually, I think it makes more sense for me to write that. Write that here than 20 log of 10. Let's call this a constant k, origin 0, and then I don't know if you recognize these yet as simple poles, but if you remember, a simple pole is 1 over, right? 1 over 1 plus s over the pole value. I'm going to assume n is equal to 1 for these two. There's no exponent down here, right? So 1 over 1 plus s over the value of the pole. This one, the value of the pole is 2. This one, the value of the pole is 10. And so this is a simple pole at s equals minus 2. This is a simple pole at s equals minus 10. And so we can go ahead and write, because we know how this looks, this value p that's here, for the simple pole. Oh, sorry, we're not talking about the phase yet. We're talking about the magnitude. It's going to go 0, 0, 0, 0, 0. This is 0 dBs. And then right at the value of the pole that we found, it's going to start dropping at 20 dBs per decade. Okay, so we have 2 of those, and we have to take care of both of them. So let's first sketch the pole at s equals minus 2. The value here is just 2. So I'm going to go 0, 0, 0, 0, 0. And then at 2, it starts dropping at 20 dB per decade. So 1 decade higher would be 20. Another decade would be 200. And so, if you couldn't tell, I already set up these axes to be very friendly to what we needed to do here. And then the next one is the exact same thing, except the value here, the p value here is 10. And so at 10, I have a value there. A decade later, it's going to be at 100, and then another decade later, it's going to be at 1,000. And so those are our 4 factors now, all plotted, right? We've plotted all 4 of our factors. And so now what's left to do to actually construct the magnitude plot of basically the contributions of all 4 of them is to just add their effects, okay? And so at every frequency interval, I basically just want to look at what's happening in that interval, right? In the first interval, I have a constant of 20 dB, and I have a negative that slopes up to 0. So right at this value, right, I have 0 from the first simple pole, 0 from the second simple pole, 0 from the origin 0, and then I have 20 dB. So right at this value, I should be at 20 dB. So all I need to do is take this 20 dBs and kind of subtract this little segment from it. And so that's what I should have right there. So I'm going to draw that. And again, I think it should be right there. Okay. And so now from here, I have, what do I have here? I have basically no more contribution from the 20 dB. I have an increase that's still happening from the origin 0, and the other 2 poles are still at 0. So this is just going to keep increasing up until it hits whatever value it hits right here at 2, omega equals 2. And then from this point forward, now I have 20 dB flat, and then I have a pole and a 0 canceling each other. So the slope is going to even out, right? I have a flat value, a plus 20 dB per decade, and a minus 20 dB per decade. And those are all going to cancel out all the way up until omega equals 10, where something new happens. What's new that happens? Well, my original origin 0 and my first pole are still canceling, but now I get contributions from this second pole that are actually going to pull this down at 20 dB per decade. So now I need to account for that. And that's the last thing that happens that causes any kind of change in my magnitude plot. So I'm just going to sketch that all the way off. And I'm going to go and label this as 20 dB per decade here. This is minus 20 dB per decade here. And that red plot now, that is the magnitude plot for this transfer function, right? And we derived it just by looking at each individual term, sketching the contributions of each individual term, right? Each one has its own contribution, and then adding their effects together at each interval of interest. And so when I talk about intervals of interest, I'm basically just saying, so within this interval, I have, all these flat lines, and I have this one increasing, and nothing else happens, right? Actually, it's all the way up until this point where that's the case. And so that's why if I add those three effects, I get 0 plus 20 dB plus this trace here, and that's what results in this this trace right here. Then at a value of omega equals 2, I get a new contribution from a new pole, and then I have to reassess. So now I have pole and a 0 canceling, and I have my flat 20 dB per decade, so the overall effect is just no slope, so it just stays constant. And then at omega equals 10, I get contributions from another pole. My original pole and my original 0 are still canceling, and this new pole starts bringing the overall magnitude response down. And then after this, nothing else changes, right? This pole and this 0 keep canceling. This stays flat, and this keeps pulling the response down. So I am left with this magnitude plot when all is said and done. Okay, so I just wanted to, again, if you have questions about this, I know that this stuff is probably pretty confusing, but I'm going to do the phase, and I'm also going to do another example, so hopefully the process becomes pretty clear. I'm going to go ahead and end this video here. I should probably label these two. This is from the pole at s equals minus 2, and this is from the pole at s equals minus 10. Okay, so I'm going to go ahead and end this video, and in the next video we're going to go ahead and do the same thing, but we're going to do it for the phase for this same transfer function. All right.